So today I want to cover another important topic. It's called a electric circuit. This topic, electric circuit. First, we need to review the basic knowledge. Second, to solve the problems. So the word problems related to electric circuit. And also related to the topic of our part C, exact ODEs. So we need to we are going to solve the called extended exact ODEs, extended. Because if we work on the original equation, it won't be exact ODEs. It does not follow the criteria we saw last time. There is a condition. We need to check that condition, but it's not satisfied. But we can find a way to make it satisfy that criteria. So that's why we do an extra step to make it exact after some smart transformation. So that's why we call the name extended exact ODEs. Just like, remember last time we learned extend separable ODEs, right? It's not separable, but we made some smart transformation to make it separable. Here, the same idea. All right, so let's start. First, I want to review some basic knowledge of electric circuit. All right. Understand electric circuit. So this is a simple diagram of electric circuit. In this diagram, you can see there are three basic components in a typical electric circuit. So first, when we say electric circuit, we mean a path for transmitting electric current. So here, the current we cannot draw, right? But we need to imagine the current flows through an electric circuit. So in our discussion, so we will talk about the current. All right. Three types of components. The first type component, electromotive force. So we use capital EMF to represent the first component. So this component, provides the power, right? So, the power, the source of the power. Okay, a device that gives energy to the charged particles constituting the current, such as a battery or generator. There are two types of EMF. The first type is the battery type. Here you can see in our diagram, 12V battery. So that's the first type. Second type, generator. Okay, generator. Another type. So not the battery, but it can generate the, electric energy. Second component, devices that use current. All right. Devices. Consume. Such as lamps. Here, lamps. Electric motors or computers. The third type, connecting wires. All right. The basic components. Then let's look at electric current. The current. Understand the current. Okay. All right. A flow of charged particles. The particles, typically, these two cases, one electrons, the particles. Second type, ions, those ions, yeah, you know, more general situation, yeah, because sometimes there is another type of electric charges, not in the electron form. So the atom, think about one atom, under the normal condition, there is no charge, right? Yeah, one atom. Yeah. But under some special condition, situation, that atom may lose an electron. Lose an electron. Okay, yeah. One electron, gone. Yeah. Then this particle has the electric charge, or another case is gain an electron. Yeah, lose or gain an electron. So then this particle has the electric charge. Yeah. So the particles with electric charge, move, through the electric circuit. Yeah. Also can cause the current. Yeah. The current formed by ions. Yeah. All right. So here you can see the ions could carry negative charges or positive charges. Okay? Yeah. Negative or positive charges. Yeah. If it loses one electron, then it's positive charge, right? If it gains one electron, then negative. We know negative electron has negative charge. So if it gain one, then it has one negative electric, charge. Yeah. But it's also possible one atom can gain several electrons, lose or gain several electrons. That's also possible. Yeah. All right. So that's about the electric current. Then another important concept we need to discuss. Tavia? Good. Okay. Yeah. So I'll check your name in the break time. Yeah. All right. Volt. This concept. Volt. Yeah. The unit. Yeah. Important. The unit. Volt. Yeah. All right. The unit of electric potential. Electric potential. Okay. That concept. Yeah. Potential. Yeah. But electric potential. Okay, I hope you have the basic knowledge of this, electric potential. Yeah, potential. First, the potential meaning, right? Yeah, electric and electric potential difference, voltage. Okay, voltage, and electric motive force. Yeah. All right. So here, let me explain in this way. Yeah. Related to this concept here, okay? Here there is a volt concept and a voltage concept. Yeah, let me explain together. That volt concept, that's the unit, right? Yeah. So when you need to describe the voltage, amount of voltage, you need to use certain unit. So that unit we use volt unit. Yeah. So what is that voltage? Yeah, we frequently use this voltage concept in our, discussion of the electric circuit. Yeah. There are two meanings when we use voltage. Yeah. There are two meanings. Sometimes you use this meaning. Sometimes you use the other meaning. Yeah. The first meaning, voltage, just electric potential. Okay? Electric potential, it refers to electric potential, the voltage. Okay? All right, for example, these 2 points. For these 2 points, yeah, so here I'm talking about in the battery. Yeah, for the Zoom students, here I'm talking about in this battery, we look at these 2 points. They have different electric potentials, right? Yeah. One higher, one lower. Yeah. So they have different electric potentials. Yeah. But people also can talk about the voltage at this point, voltage at that point, because it has the meaning electric potential. Okay, yeah, that's the first meaning. The second meaning is the difference of the electric potential. Yeah, we can call it voltage. The difference, yeah, difference of two potential. Yeah. So here, yeah, but here in later in our discussion, in order to, make it clear, in our textbook, in many places, it's called voltage drop. Okay, voltage drop. Yeah. Then that voltage there, that's the electric potential, right? Potential drop, electric potential drop. That's the difference. So when it refers to where later in our questions, when it refers to voltage drop, the difference of the potential, right? Yeah, yeah. Here. All right. Yeah, but sometimes people may not add that drop, just call it voltage, but it can also be understood as the difference of the potential. Okay, yeah, just yeah. All right, so this slide. Yeah. Next, basic concepts in electric circuit. Yeah. After that, then we need to understand the typical objects we used in electric circuit. Yeah. All right, look at a typical diagram of an electric. Yeah. So in our diagram, we use symbols to represent different devices. Yeah. Symbols. Yeah. Those symbols are standard symbols. Okay, standard. Yeah. Yeah. So everyone must use the same symbols, yeah, for the communication. Yeah. All right. The first concept, inductor concept. Yeah. So very important device in electric circuit. Inductor. So that is a passive two-terminal electrical component. Yeah. Passive. It consumes electric energy, right? Yeah. It does not generate electric energy. It consumes electric energy. Okay. So it's passive. Passive, all right, that stores energy in the magnetic field. Magnetic field, think about it. Yeah. So this structure, yeah, when you provide electric current there, this component can generate a magnetic field. Okay? Magnetic field. So there is a theorem. Okay? Yeah. There is a law. Yeah, let's say law. There is a law describe that phenomenon. Okay? The electric current, moving through that coil can generate a magnetic field. All right, that's an important law. All right, yeah. So that an inductor typically consists of an insulated wire. Yeah. So look at this wire, insulated wire. Yeah. Wound into a coil. Okay. Yeah. Yeah. You have to, use this coil shape. Yeah. In this way, magnetic field can be generated. Okay? Yeah. So this phenomenon is very important. Yeah. In electric circuit. All right. Second, another important device, capacitor. Capacitor. Like that. Yeah. So the capacitor component, yeah, is an electronic device that stores electrical energy in an electric field by accumulating electric charges on two closely spaced surfaces. Yeah. So in this, cylindrical shape inside, you can inside two surfaces, yeah, two closely spaced surfaces, yeah, that are insulated from each other. Yeah. That structure can hold electronic charges. Yeah. Electronic charges. Okay? Yeah. So it has the property. Yeah. This capacitor can hold certain amount of electric charges. Yeah. Another important component. Yeah. All right. Capacitor. In this diagram, the C, okay, the symbol, okay. So one vertical bar, another bar, curved vertical bar. Yes, small curve here. Okay, yeah, yeah. All right. Then, yeah, here it is a passive electronic component with two terminals. Yeah, yeah. Passive. Okay, yeah. All right, yeah. Then the third one, resistor component, R, okay, resistor, yeah, component. Yeah. All right, a passive electrical component with the primary function to limit the flow of the electric current. Yeah. Yeah. When you add a certain number of resistors, yeah. So here, resistors in your electric circuit, so you can slow down, limit, okay, yeah, limit. So you add something to limit the electric current. Yeah. All right, and a lot of devices, yeah. So a lot of electric devices, so they have certain amount of resistor, yeah. All right, measure. Yeah, we'll talk about measure. Next slide. All right. So then we need to understand the basic laws. Yeah. So after we understand these components, then there are some basic laws we need to use when we model an electric circuit. Yeah. All right, so next slide, let's look at the basic laws. Yeah. All right, yeah, so this table, yeah, so three basic laws here. Yeah, so let me explain one by one. Okay, all right. So we need to use these three laws to set up differential equation, ODE differential equation. Yeah, but yeah. So after this slide, we will look at our first question in electric circuit. Yeah. All right. The first law, Ohm's law. Yeah. Ohm's law states. Yeah. So let's use this line to understand Ohm's law. Okay. Yeah. The first line. Ohm's law states that the electric current through a conductor between 2 points. Yeah. Here, let's consider a conductor here. Yeah. So we use this part. Yeah. Suppose we are talking about this part. Okay. Yeah. The conductor. Then we consider 2 points. These 2 points. Yeah. 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 Around this conductor. Okay. So there is some resistor. Okay. Yeah. All right. So here, that states that the electric current through current. So here, yeah, there is a. So here we want to use this current. Current, we use I. Represent current. Okay. So here are I. And R, resistor, this R. Okay? And the resistance, we call it resistance. Yeah. In the unit ohm, so this capital omega we call it ohms. ohm, okay? Capital omega, ohms, yeah. All right. So then the electric current directly proportional to the voltage across the 2 points. Yeah. Here, voltage across, so here we use that concept, voltage. Yeah, usually we use capital V, represent the voltage. Okay? Voltage across the point. Because these 2 points, each one has a electric potential, right? This point has an electric potential. There is a difference between these 2 electric potentials, right? Yeah. So that voltage is the difference of those 2 electric potentials. Yeah. So here you can see, here we use voltage, we mean the difference of the potentials. Okay? Difference of the potentials. Yeah. Or voltage drop. Okay. Later in our question, we use voltage drop. But here we do not use voltage drop. We use voltage, yeah, because it has the difference meaning. Difference of 2 potential, the meaning. Yeah. All right. So it's directly proportional. Okay? Directly proportional. What's that? Yeah. That means, sorry, I need to write it here. That means the voltage, here it uses voltage drop, right? Yeah, here it uses voltage drop. But here it just uses voltage. Okay? All right. V equals a constant R here, because the meaning of directly proportional, this means a constant, right? You need to multiply. So this means directly proportional. That means this I equals some constant. Yeah, constant. Okay? Constant times V. Okay? Constant times V. But what's that constant? What's that constant? Yeah. Here, from this formula, you can see that constant is 1 over R. Okay? That constant, yeah. So we can write 1 over R. Resistance times the voltage V. Okay? Yeah. So that's the Ohm's law. Okay? Ohm's law described in this way. Okay? Yeah. But this way is equivalent to Ohm's law, right? That is the original form of the Ohm's law. Okay? Yeah. Because Ohm discovered this law by a lot of experiments. Yeah. So in Ohm's original form of the theorem, the formula is like this. Okay? Yeah. I equals certain constant, so 1 over R, certain constant times that V. Yeah, but here, because usually people like to use this form, yeah, because there is no denominator, right? So this is the most commonly used way of Ohm's law. Okay, V equals R times I. Yeah, yeah. Although slightly different from the original Ohm's law, yeah, but equivalent. Yeah, yeah. So that's why, yeah, voltage drop equals R times I. That's the first theorem, basic theorem. Yeah. Law. Yeah. In physics we call law. In math we call it theorem. Yeah. That's different. Yeah. All right. Yeah. That is the equivalent form. Okay. All right. Then another important basic law about inductance. Inductor. Huh? Regarding the inductor, yeah, the coil, yeah, thing, yeah. So then there is another law. Inductance is defined as the ratio of the induced voltage to the rate of change of current causing it. Yeah. All right, so let's try to understand. So the second the second law, we use the second law to understand the second law. Okay, second law. Yeah. All right, ratio. Yeah, how to define inductance? So here, this one, give us the way to define inductance. Yeah. How to define? Yeah. Define as a ratio of two quantities. Yeah. The first quantity, call it induced voltage. Induced voltage, yeah. Because when electric current goes through, that coil, that structure, that inductor, yeah. So a certain voltage is induced, yeah. To the new denominator rate of change of the current. So what's the rate of change of the current? Yeah. Derivative. We know rate of change, it's derivative, right? Yeah. So the rate of change of the current, that's the I prime. Okay? Yeah. I current is a function of t, right? Time. I, the current, is a function of time t. Yeah. At different time, the current is different. Okay? The amount of current is different. So there is a rate of change, I, capital I prime. That's the rate of change of the current. Yeah. Yeah. All right, so here we use the di over dt. Okay? Yeah, di over dt, the rate of change. Yeah. All right. Yeah. So here, this statement tells us. Yeah. So although, yeah. So here, yeah, we call it. It's a law. It's a law. Yeah. So here, let me use the statement temporarily. Yeah. Later, we move to law. Okay. All right. So this statement tells us. Yeah. Yeah. Actually, this formula V equals L times di over dt. That is the law formula, okay? But what is L, right? Yeah, so what is L? So this statement tells us what is the L, okay? L, that's the notation for this inductance. Yeah. What's the L? Yeah. L is so here, inductance, right? Yeah, L. So L here. Yeah, notation for that inductance. But the question is, how do you define that inductance, right? Yeah? So in physics, when you introduce a concept, here the concept is called inductance. But how do you define that inductance concept, right? So this statement defines the inductance concept. How to define? Yeah. So let me translate this statement. So this statement tells us the inductance L is defined as a ratio of two quantities. Okay, the ratio numerator is the V, voltage, induced voltage. Yeah. The denominator is the rate of change of the current. That's the definition. Okay, so this statement tells us how to define the inductance, yeah, V over I prime. Okay? Yeah. I prime. Yeah. All right. So that formula just the equivalent form. Okay? Yeah. Equivalent form. Yeah. All right. Yeah. All right. So the unit Henrys. Henrys, yeah. Another important physician, Henry, yeah. Then the last one, last basic law that we need to use in this class, capacitor. Then we need a related law That is, every isolated conductor exhibits capacitance called self-capacitance. Yeah. All right. So then it is measured by the amount of electric charge. Yeah. Because that capacitor can hold certain amount of electric charge. Yeah. All right. So we use that amount of electric charge. All right. That must be added to an isolated conductor to raise its electric potential by 1 volt. Yeah. So this is 1 unit. Yeah. 1 volt. Yeah, that's the unit, right? Yeah. 1 V. Yeah. Yeah. So volt, we use that V. Okay. Yeah. 1 volt. Yeah. V. All right. Yeah. To understand that. Yeah. So here, let me use this diagram to understand the meaning. Use this diagram. Okay. Yeah. So this capacitor can hold certain amount of electric charge, right? Yeah, yeah. All right. So think in this way. Yeah. You can add electric charge to that capacitor, right? Yeah. You can add more electric charge. Okay. All right. When you add more electric charge, the voltage will be higher, right? Yeah. The voltage between these 2 points, yeah, because these two, these 2 points, they have different electric potentials, right? Yeah. The potential difference, that's the voltage. But when you add more electric charge to this capacitor, the voltage will be higher, right? Yeah. The voltage will be higher. Okay? All right. So now, yeah. So how do we measure capacitance? Yeah. We need a unit, right? The capacitance. We need to define a unit. Amount of capacitance. Yeah. So that unit is defined in this way. Okay? All right. All right. So when you add certain amount of electric charge to increase the voltage by 1 V. Yeah. So when you add, so you measure it. Okay. Certain amount of electric charge, then the voltage is 1 V higher. 1 V higher. Yeah, okay? So that amount of electric charge, we use it to define that capacitance. Okay? We use that amount of, yeah. Because for different capacitor, that amount is different. Yeah. Yeah. So, yeah, because for different capacitors, yeah, that capacitance is different. Okay? Yeah. So you define in that way. The unit is farads. Yeah. F, farads. Yeah. All right. Yeah. That's pretty much what we need for the basic components. All right. Yeah. Yeah. Basic components. Yeah, because when we work on one electric circuit, so these 3 types, that's all our basic components in an electric circuit. Okay? Yeah. But you can see these 3 types, we use these 3 laws to calculate the voltage drop around each component. Voltage drop around each component. So it's a local description, right? Yeah. Only around that particular component locally. It's not a global description, right? Yeah, so these 3 laws are local descriptions. Yeah. But when we do the modeling, we need a global law. Okay? If we only have local law, we cannot set up equation, right? Yeah. So we can represent local voltage drop everywhere, right? But we don't have equation, right? So globally, we don't have equation. Yeah. So in order to set up one equation covering the whole electric circuit, we need a global law. Okay? Yeah. All right. Yeah. So the basics, now we complete the review, the basic knowledge before we work on electric circuit. Yeah. So we rely on this basic understanding, yeah, to solve any given electric circuit. All right. Yeah. Any question? Yeah. Before we move to solving a real problem example. Yeah. All right. Yeah. So let's use our next electric circuit question to help us understand these concepts better. Okay. All right. Yeah, here, right. Yeah. So this because voltage drop, you write volt here. Yeah. So here, one more thing. Yeah. This quantity, Q, amount of electric charge, that capital Q, amount of electric charge, yeah, we use the unit, so the capital C unit, Coulomb, yeah, Coulomb, yeah. Capital C, yeah, Coulomb, yeah. Yeah. All right. Yeah, so let's go to C.3. Yeah. Yeah. And when we work on electric circuit, there are several types. Yeah. So remember, we have three basic components, right? R-type component, L-type component, and a C-type component. Okay. So R, L, C. Yeah. Three-type component. Yeah. So our first example, so we call it RL circuit. Yeah. So no C. Yeah. So only, resistor and inductor. Yeah. These two types components. Yeah. All right. Yeah. Yeah. First, let's look at a simple electric circuit. Yeah. The electromotive here, E equals 48V. Yeah. So that E, either a battery, a generator. Yeah. So, here we just, get that E. Yeah. EMF. Yeah. EMF, but here we use symbol E here. E equals 48V. Yeah. Then there is one resistor with 11 ohms and one inductor with 0.1 Henry. Yeah. So let's look at the question. Yeah. Very simple example. Yeah. All right. Model the RL circuit in figure 19 and solve the resulting ODE for the current I of t that amount of capital A amperes. Yeah, that amount of amperes, capital A. Yeah. Yeah, but where t is the time, yeah, assuming that the circuit contains as an EMF E of t, yeah, E of t. So the general EMF E of t is a function of t, but in this question, it's a constant, yeah, 48V, yeah. But in other questions, you may get a function, okay, yeah. So it may not be a constant, yeah, yeah. All right. Yeah. So which is constant, resistor of R, 11 ohms, inductor of L, 0.1 Henries, and that the current initially 0. All right? Yeah. Think about it. At the time 0, the current is 0. Okay? Yeah. The current is 0. Yeah. So that means you do not connect. You do not connect that EMF. Yeah. Then your clock. Yeah. So look at the clock. When you start, you're connected. Okay? Yeah. Yeah. So start at time 0, then you connect E. Okay? You connect E, so there is a force, right? Yeah. But electric current changes from 0 to I of t. Yeah, there is a change. Yeah. T. Yeah. So here the question is how to calculate that I function. I of t, it changes. Yeah. At 0, it is 0, but after you connect it, yeah, it will be non-zero. Right? It will change, yeah, as a function of time. Yeah. But we need to find that function of I. That's the question. Okay? All right. So then, to solve this problem, we need to we need a physical law, as I mentioned, the global law, to help us model the whole system. So it's a system, yeah, the whole system. But we do not have a global law to describe the whole system. So we need such a law, physical law. Okay, all right. So we call the Kirchhoff's voltage law, KVL. Okay, yeah. Kirchhoff's voltage law, yeah, gives us the global description about the system. Yeah. So what's that? Yeah. It's very simple. Yeah. It says the voltage, the electromotive force, yeah, the voltage provided by the electromotive force, EMF. Yeah? That E function, the voltage. Yeah. So that's the force part. That force part, yeah, power the whole electric circuit, right? Yeah. That other than that component, it powers the electric circuit. Then the remaining components consume the electric energy, right? The remaining devices consume the electric energy. Yeah. So then, so this voltage impressed on a closed loop is equal to the sums of the voltage drops across all the other elements of the loop. Yeah. All right. So here we have two components, right? Yeah. Other than the EMF. Yeah. EMF. Yeah. So there is a voltage. Yeah. But when we go through all the other components, there are some voltage drops, right? Yeah. Voltage drops twice. Okay. Yeah. When electric current passes the first component, there is first voltage drop. Passes the second component, there is a second voltage drop. Okay? But sum of these two voltage drops, add these two voltage drops, then we get the EMF, that voltage. The voltage provided by EMF. That's the Kirchhoff voltage law. Okay? Kirchhoff voltage law. Yeah. All right, so now we can set up an equation by Kirchhoff voltage law. Yeah. All right. Yeah. So the voltage drop for the first component, that's R times I. Okay? V1, yeah, if we call it V1, okay? R times I. The second one, yeah, L times derivative of I, right? Yeah. Remember our second basic law, R, that V, the voltage drop, equals L times rate of change of the current. Yeah. So the second, V2, yeah, V2 equals L times di over dt. Okay, yeah. So we add up these two voltage drops equals 48. How about that? Yeah? Yeah. So the equation is pretty straightforward. Equation is E equals L, capital L times capital I prime plus capital R times capital I. See? It's a simple equation. Yeah, right? In this equation, let's look at the knowns and unknowns. Yeah. Knowns and unknowns in this equation. Yeah. E is known, right? 48. E is known. L is known. 0.1 given, Henry. 0.1 Henrys. Okay? All right. R also given. 11 ohms given. Okay? So the only unknown quantity is the electric current I, capital I, as a function of time t. That's unknown. Okay? So here we just solve an ODE, yeah. Simple ODE, yeah, yeah, with one unknown function. I function is unknown. Yeah, yeah. So we can plug in the known numbers, yeah, so we can see that explicit. Yeah. So here, because we want to write as a, more friendly form, right? Yeah. I prime, the first term, the second term, some constant times I, then the right-hand side, another constant. Okay? Yeah. So we can plug in the number, yeah, after simplification, yeah. Because usually we like to use y to represent unknown function, right? Although you don't have to, you can keep using I, but for many of us, we like to make the unknown function y. Okay, we are more familiar with that form. Okay, yeah. So here you can see, after simplification, we get a simple first order ODE. First order ODE. Yeah. Y prime plus 110 y equals 480. Okay, 480. Yeah. All right. Yeah. So this one, can you solve it? Yeah. This one, is it a separable one? Separable, right? Is this separable ODE? It's a simple separable ODE, right? Yeah. Yeah. So you can solve it in a simple separable ODE. Right? Yeah. 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 So if you solve it in a that simple separable ODE, yeah, that's all we need, right? That's all we need. Yeah. But here, although we can solve it by separable ODE, yeah, but we like to use this simple example to help us to extend that exact ODE. Yeah, that one. Okay? Yeah. Because although it's not necessary, but for the learning purpose. Okay? So here for the learning purpose, right? Here it's not in the real world problem solving. Real world, you use separable ODE. Then you're done, right? Yeah. But here, we want to learn another important problem solving tool, right? So how about we just use this simple example to help us develop another useful problem solving tool. Okay? All right. So let's take a 10-minute break.